Part 2, Chapter 6 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Chapter 6, The Sun's Distance. The question of the sun's distance arises naturally from the consideration of his temperature, since the intensity of the radiations emitted, as compared with those received and measured, depends upon it. But the knowledge of that distance has a value quite apart from its connection with solar physics. The semi-diameter of the earth's orbit is our standard measure for the universe. It is the great fundamental datum of astronomy, the unit of space, any error in the estimation of which is multiplied and repeated in 1,000 different ways, both in the planetary and sidereal systems. Hence its determination was called by Airy the noblest problem in astronomy. It is also one of the most difficult. The quantities dealt with are so minute that their sure grasp tasks all the resources of modern science. An observational inaccuracy which would set the moon nearer to or farther from us than she really is by 100 miles would vitiate an estimate of the sun's distance to the extent of 16 million. What is needed in order to attain knowledge of the desired exactness is no less than this: to measure an angle about equal to that subtended by a halfpenny 2,000 feet from the eye, within a little more than 1,000th part of its value. The angle thus represented is what is called the horizontal parallax of the sun. By this amount, the breadth of a halfpenny at 2,000 feet, he is to a spectator on the rotating earth, removed at rising and setting from his meridian place in the heavens. Such, in other terms, would be the magnitude of the terrestrial radius as viewed from the sun. If we knew this magnitude with certainty and precision, we should also know with certainty and precision the dimensions of the earth being, as they are well ascertained, the distance of the sun. In fact, the one quantity commonly stands for the other in works treating professedly of astronomy. But this angle of parallax, or apparent displacement, cannot be directly measured, cannot even be perceived with the finest instruments. Not from its smallness. The parallactic shift of the nearest of the stars, as seen from opposite sides of the earth's orbit, is many times smaller. But at the sun's limb, and close to the horizon, where the visual angle in question opens out to its full extent, atmospheric troubles become overwhelming, and altogether swamp the far more minute effects of parallax. There remain indirect methods. Astronomers are well acquainted with the proportions which the various planetary orbits bear to each other. They are so connected in the manner expressed by Kepler's third law, that the periods being known, it only needs to find the interval between any two of them in order to infer at once the distances separating them all from one another and from the sun. The plan is given. What we want to discover is the scale upon which it is drawn, so that if we can get a reliable measure of the distance of a single planet from the earth, our problem is solved. Now, some of our fellow travellers in our unending journey round the sun come at times well within the scope of celestial trigonometry. The orbit of Mars lies at one point not more than 35 million miles outside that of the earth, and when the two bodies happen to arrive together in or near the favourable spot, a conjuncture which occurs every 15 years, the desired opportunity is granted. Mars is then in opposition, or on the opposite side of us from the sun, crossing the meridian consequently at midnight. It was from an opposition of Mars, observed in 1672 by Richer at Cayenne in concert with Cassini in Paris, that the first scientific estimate of the sun's distance was derived. It appeared to be nearly 87 millions of miles, parallax 9.5 minutes, while Flamsteed deduced 81,700,000, parallax 10 minutes, from his independent observations of the same occurrence, a difference quite insignificant at that stage of the inquiry. But Picard's result was just half Flamsteed's, parallax 20 minutes, distance 41 million miles, and La Hire considered that we must be separated from the hearth of our system by an interval of at least 136 million miles, so that uncertainty continued to have an enormous range. Venus, on the other hand, comes closest to the earth when she passes between it and the sun. At such times of inferior conjunction she is, however, still 26 million miles, or in round numbers 109 times as distant as the moon. Moreover, she is so immersed in the sun's rays that it is only when her path lies across his disk that the requisite facilities for measurement are afforded. These partial eclipses of the sun by Venus, as Encke termed them, are coupled together in pairs, of which the components are separated by 8 years, recurring at intervals alternately of 105½ and 121½ years. Thus the first calculated transit took place in December 1631, and its companion, observed by Horrocks in the same month, in S. 1639. Then, after the lapse of 121½ years, came the June couple of 1761 and 1769, and again after 105½, the two last observed December 8, 1874, and December 6, 1882. Throughout the 20th century there will be no transit of Venus, but the astronomers of the 21st will only have to wait 4 years for the first of a June pair. The rarity of these events is due to the fact that the orbits of the Earth and Venus do not lie in the same plane. If they did, there would be a transit each time that our twin planet overtakes us in her more rapid circling, that is, on an average every 584 days. As things are actually arranged, she passes above or below the sun, except when she happens to be very near the line of intersection of the two tracks. Such an occurrence as a transit of Venus seems at first sight full of promise for solving the problem of the sun's distance, for nothing would appear easier than to determine exactly either the duration of the passage of a small dark orb across a large brilliant disk, or the instant of its entry upon or exit from it. And the differences in these times, which, owing to the comparative nearness of Venus, are quite considerable, as observed from remote parts of the earth, can be translated into differences of space, that is, into apparent or parallactic displacements, whereby the distance of Venus becomes known, and thence, by a simple sum in proportion, the distance of the sun. But in that word exactly what snares and pitfalls lie hid. It is so easy to think and to say, so indefinitely hard to realize. The astronomers of the 18th century were full of hope and zeal. They confidently expected to attain, through the double opportunity offered them, to something like a permanent settlement of the statistics of our system. They were grievously disappointed. The uncertainty as to the sun's distance, which they had counted upon reducing to a few 100,000 miles, remained at many millions. In 1822, however, Encke, then director of the Seeberg Observatory near Gotha, undertook to bring order out of the confusion of discordant and discordantly interpreted observations. His combined result for both transits, 1761 and 1769, was published in 1824, and met universal acquiescence. The parallax of the sun thereby established was 8.5776 minutes, corresponding to a mean distance of 95 1/4 million miles. Yet this abolition of doubt was far from being so satisfactory as it seemed. Serenity on the point lasted exactly 30 years. It was disturbed in 1854 by Hansen's announcement that the observed motions of the moon could be drawn into accord with theory only on the terms of bringing the sun considerably nearer to us than he was supposed to be. Dr. Matthew Stewart, professor of mathematics in the University of Edinburgh, had made a futile attempt in 1763 to deduce the sun's distance from his disturbing power over our satellite. Tobias Mayer of Göttingen, however, whose short career was fruitful of suggestions, struck out the right way to the same end; and Laplace, in the seventh book of the Mécanique Céleste, gave a solar parallax, derived from the lunar parallactic inequality, substantially identical with that issuing from Encke's subsequent discussion of the 18th century transits. Thus two wholly independent methods, the trigonometrical, or method by survey, and the gravitational, or method by perturbation, seemed to corroborate each, the upshot of the use of the other, until the 19th century was well past its meridian. It is singular how often errors conspire to lead conviction astray. Hansen's note of alarm in 1854 was echoed by Leverrier in 1858. He found that an apparent monthly oscillation of the sun, which reflects a real monthly movement of the earth round its common centre of gravity with the moon, and which depends for its amount solely on the mass of the moon and the distance of the sun, required a diminution in the admitted value of that distance by fully 4,000,000 miles. 3 years later he pointed out that certain perplexing discrepancies between the observed and computed places both of Venus and Mars would vanish on the adoption of a similar measure. Moreover, a favourable opposition of Mars gave the opportunity in 1862 for fresh observations, which, separately worked out by Stone and Winecki, agreed with all the newer investigations in fixing the great unit at slightly over 91,000,000 miles. In Newcomb's hands they gave 92.5 million. The accumulating evidence in favour of a large reduction in the sun's distance was just then reinforced by an auxiliary result of a totally different and unexpected kind. The discovery that light does not travel instantaneously from point to point, but takes some short time in transmission, was made by Olaus Römer in 1675, through observing that the eclipses of Jupiter's satellites invariably occurred later, when the earth was on the far side, than when it was on the near side of its orbit. Half the difference, or the time spent by a luminous vibration in crossing the mean radius of the earth's orbit, is called the light equation, and the determination of its precise value has claimed the minute care distinctive of modern astronomy. Delambre, in 1792, made it 493 seconds. Glasenapp, a Russian astronomer, raised the estimate in 1874 to 501. Professor Harkness adopts a safe medium value of 498 seconds. Hence, if we had any independent means of ascertaining how fast light travels, we could tell at once how far off the sun is. There is yet another way by which knowledge of the swiftness of light would lead us straight to the goal. The heavenly bodies are perceived, when carefully watched and measured, to be pushed forward out of their true places, in the direction of the earth's motion, by a very minute quantity. This effect, already adverted to, has been known since Bradley's time as aberration. It arises from a combination of the two movements of the earth round the sun and of the light waves through the ether. If the earth stood still, or if light spent no time on the road from the stars, such an effect would not exist. Its amount represents the proportion between the velocities with which the earth and the light rays pursue their respective journeys. This proportion is, roughly, 1 to 10,000. So that here again, if we knew the rate per second of luminous transmission, we should also know the rate per second of the earth's movement, consequently the size of its orbit and the distance of the sun. But until lately, instead of finding the distance of the sun from the velocity of light, there has been no means of ascertaining the velocity of light except through the imperfect knowledge possessed as to the distance of the sun. The first successful terrestrial experiments on the point date from 1849, and it is certainly no slight triumph of human ingenuity to have taken rigorous account of the delay of a sunbeam in flashing from one mirror to another. Fizeau led the way, and he was succeeded after a few months by Léon Foucault, who in 1862 had so far perfected Wheatstone's method of revolving mirrors as to be able to announce with authority that light travels slower, and that the sun was in consequence nearer than had been supposed. Thus a third line of separate research was found to converge to the same point with the two others. Such a conspiracy of proof was not to be resisted, and at the anniversary meeting of the Royal Astronomical Society in February 1864, the correction of the solar distance took the foremost place in the annals of the year. Lest, however, a sudden bound of 4,000,000 miles nearer to the centre of our system should shake public faith in astronomical accuracy, it was explained that the change in the solar parallax corresponding to that huge leap amounted to no more than the breadth of a human hair, 125 feet from the eye. The Nautical Almanac gave from 1870 the altered value of 8.95 minutes, for which Newcomb's result of 8.85 minutes, adopted in 1869 in the Berlin Ephemeris, was substituted some 10 years later. In astronomical literature, the change was initiated by Sir Edmund Beckett in the first edition, 1865, of his Astronomy without Mathematics. If any doubt remained as to the misleading character of Encke's deduction, so long implicitly trusted in, it was removed by Powalke's and Stone's rediscussions in 1864 and 1868, respectively, of the transit observations of 1769. Using improved determinations of the longitude of the various stations, and a selective judgment in dealing with their materials, which, however indispensable, did not escape adverse criticism, they brought out results confirmatory of the no longer disputed necessity for largely increasing the solar parallax, and proportionately diminishing the solar distance. Once more in 1890, and this time with better success, the 18th century transits were investigated by Professor Newcomb. Turning to account the experience gained in the interim regarding the optical phenomena accompanying such events, he elicited from the mass of somewhat discordant observations at his command a parallax 8.79 minutes, in close agreement with the value given by sundry modes of recent research. Conclusions on the subject, however, were still regarded as purely provisional. A transit of Venus was fast approaching, and to its arbitrament, as to that of a court of final appeal, the pending question was to be referred. It is true that the verdict in the same case by the same tribunal a century earlier had proved of so indecisive a character as to form only a starting point for fresh litigation. But that century had not passed in vain, and it was confidently anticipated that observational difficulties, then equally unexpected and insuperable, would yield to the elaborate care and skill of forewarned modern preparation. The conditions of the transit of December 8, 1874, were sketched out by Sir George Airy, then Astronomer Royal, in 1857, and formed the subject of eager discussion in this and other countries down to the very eve of the occurrence. In these Mr. Proctor took a leading part, and it was due to his urgent representations that provision was made for the employment of the method identified with the name of Halley, which had been too hastily assumed inapplicable to the first of each transit pair. It depends upon the difference in the length of time taken by the planet to cross the sun's disk, as seen from various points of the terrestrial surface, and requires accordingly the visibility of both entrance and exit at the same station. Since these were, in 1874, separated by about 3½ hours, and the interval may be much longer, the choice of posts for the successful use of the method of durations is a matter of some difficulty. The system described by Delisle in 1760, on the other hand, involves merely noting the instant of ingress or egress, according to situation, from opposite extremities of a terrestrial diameter, the disparity in time giving a measure of the planet's apparent displacement, hence of its actual rate of travel in miles per minute, from which its distances severally from earth and sun are immediately deducible. Its chief attendant difficulty is the necessity for accurately fixing the longitudes of the points of observation, but this was much more sensibly felt a century ago than it is now, the improved facility and certainty of modern determinations tending to give the Delislean plan a decided superiority over its rival. These two traditional methods were supplemented in 1874 by the camera and the heliometer. From photography, above all, much was expected. Observations made by its means would have the advantages of impartiality, multitude, and permanence. Peculiarities of vision and bias of judgment would be eliminated. The slow progress of the phenomenon would permit an indefinite number of pictures to be taken, their epochs fixed to a fraction of a second, while subsequent leisurely comparison and measurement could hardly fail, it was thought, to educe approximate truth from the mass of accumulated evidence. The use of the heliometer, much relied on by German observers, was so far similar to that of the camera that the object aimed at by both was the determination of the relative positions of the centres of the sun and Venus viewed at the same absolute instant from opposite sides of the globe, so that the principle of the two older methods was to ascertain the exact times of meeting between the solar and planetary limbs; that of the two modern to determine the position of the dark body already thrown into complete relief by its shining background. The former are methods by contact, the latter methods by projection. Every country which had a reputation to keep or to gain for scientific zeal was forward to co-operate in the great cosmopolitan enterprise of the transit. France and Germany each sent out 6 expeditions. 26 stations were in Russian, 12 in English, 8 in American, 3 in Italian, 1 in Dutch occupation. In all, at a cost of nearly $250,000, some 80 distinct posts of observation were provided; among them such inhospitable and all but inaccessible rocks in the bleak southern ocean as St. Paul's and Campbell's Islands, swept by hurricanes, and fitted only for the habitation of sea birds, where the daring votaries of science, in the wise prevision of a long leaguer by the elements, were supplied with stores for many months or even a whole year. Siberia and the Sandwich Islands were thickly beset with observers. Parties of 3 nationalities encamped within the mists of Kerguelen Island, expressly termed the Land of Desolation, in the sanguine, though not wholly frustrated hope of a glimpse of the sun at the right moment. M. Janssen narrowly escaped destruction from a typhoon in the China Seas on his way to Nagasaki. Lord Lindsay, now Earl of Crawford, and Balcarres equipped at his private expense an expedition to Mauritius, which was in itself an epitome of modern resource and ingenuity. During several years, the practical methods best suited to ensure success for the impending enterprise formed a subject of European debate. Official commissions were appointed to receive and decide upon evidence, and experiments were in progress for the purpose of defining the actual circumstances of contacts, the precise determination of which constituted the only tried, though by no means an assuredly safe road to the end in view. In England, America, France, and Germany, artificial transits were mounted, and the members of the various expeditions were carefully trained to unanimity in estimating the phases of junction and separation between a moving dark circular body and a broad illuminated disk. In the previous century, a formidable and prevalent phenomenon, which acquired notoriety as the black drop or black ligament, had swamped all pretensions to rigid accuracy. It may be described as substituting adhesion for contact, the limbs of the sun and planet, instead of meeting and parting with the desirable clean definiteness, clinging together as if made of some glutinous material, and prolonging their connection by means of a dark band or dark threads stretched between them. Some astronomers ascribed this baffling appearance entirely to instrumental imperfections, others to atmospheric agitation, others again to the optical encroachment of light upon darkness known as irradiation. It is probable that all these causes conspired in various measure to produce it, and it is certain that its conspicuous appearance may, by suitable precautions, be obviated. The organization of the British forces reflected the utmost credit on the energy and ability of Lieutenant Colonel Tupman, who was responsible for the whole. No useful measure was neglected. Each observer went out ticketed with his personal equation, his senses drilled into a species of martial discipline, his powers absorbed, so far as possible, in the action of a cosmopolitan observing machine. Instrumental uniformity and uniformity of method were obtainable and were attained, but diversity of judgment unhappily survived the best directed efforts for its extirpation. The eventful day had no sooner passed than telegrams began to pour in, announcing an outcome of considerable, though not unqualified success. The weather had proved generally favourable. The manifold arrangements had worked well, contacts had been plentifully observed, photographs in lavish abundance had been secured. A store of materials, in short, had been laid up, of which it would take years to work out the full results by calculation. Gradually, nevertheless, it came to be known that the hope of a definitive issue must be abandoned. Unanimity was found to be as remote as ever. The dreaded black ligament gave indeed less trouble than was expected, but another appearance supervened which took most observers by surprise. This was the illumination due to the atmosphere of Venus. Astronomers, it is true, were not ignorant that the planet had, on previous occasions, been seen girdled with a lucid ring. But its power to mar observations by the distorting effect of refraction had scarcely been reckoned with. It proved, however, to be very great. Such was the difficulty of determining the critical instant of internal contact that, in Colonel Tupman's words, observers side by side with adequate optical means differed as much as 20 or 30 seconds in the times they recorded for phenomena which they have described in almost identical language. Such uncertainties in the data admitted of a corresponding variety in the results. From the British observations of ingress and egress, Sir George Airy derived in 1877 a solar parallax of 8.76 minutes, corrected to 8.754 minutes, indicating a mean distance of 93,375,000 miles. Mr. Stone obtained a value of 92 millions, parallax 8.88 minutes, and held any parallax less than 8.84 minutes or more than 8.93 minutes to be absolutely negatived by the documents available. Yet from the same, Colonel Tupman deduced 8.81 minutes, implying a distance 700,000 miles greater than Stone had obtained. The best French observations of contacts gave a parallax of about 8.88 minutes. French micrometric measures the obviously exaggerated one of 9.05 minutes. Photography, as practiced by most of the European parties, was a total failure. Utterly discrepant values of the microscopic displacements designed to serve as sounding lines for the solar system issued from attempts to measure even the most promising pictures. "You might as well try to measure the zodiacal light," it was remarked to Sir George Airy. Those taken on the American plan of using telescopes of so great focal length as to afford, without further enlargement, an image of the requisite size, gave notably better results. From an elaborate comparison of those dating from Vladivostok, Nagasaki, and Peking, with others from Kerguelen and Chatham Islands, Professor D.P. Todd of Amherst College deduced a solar distance of about 92 million miles, parallax 8.883 minutes, plus or minus 0.034 minutes, and the value was much favored by concurrent evidence. On the whole, estimates of the great spatial unit cannot be said to have gained any security from the combined effort of 1874. A few months before the transit, Mr. Proctor considered that the uncertainty then amounted to 1,448,000 miles. 5 years after the transit, Professor Harkness judged it to be still 1,575,950 miles, yet it had been hoped that it would have been brought down to 100,000. As regards the end for which it had been undertaken, the grand campaign had come to nothing. Nevertheless, no sign of discouragement was apparent. There was a change of view, but no relaxation of purpose. The problem, it was seen, could be solved by no single heroic effort, but by the patient approximation of gradual improvements. Astronomers accordingly looked round for fresh means or more refined expedients for applying those already known. A new phase of exertion was entered upon. On September 5, 1877, Mars came into opposition near the part of his orbit which lies nearest to that of the earth, and Dr. Gill, now Sir David, took advantage of the circumstance to appeal once more to him for a decision on the quaestio vexata of the sun's distance. He chose as the scene of his labours the island of Ascension, and for their plan a method recommended by Airy in 1857, but never before fairly tried. This is known as the diurnal method of parallaxes. Its principle consists in substituting successive morning and evening observations from the same spot for simultaneous observations from remote spots, the rotation of the earth supplying the necessary difference in the points of view. Its great advantage is that of unity in performance. A single mind looking through the same pair of eyes, reinforced with the same optical appliances, is employed throughout, and the errors inseparable from the combination of data collected under different conditions are avoided. There are many cases in which one man can do the work of two better than two men can do the work of one. The result of Gill's skilful determinations made with Lord Lindsay's heliometer was a solar parallax of 8.78 minutes, corresponding to a distance of 93,080,000 miles. The bestowal of the Royal Astronomical Society's gold medal stamped the merit of this distinguished service. But there are other subjects for this kind of inquiry besides Mars and Venus. Professor Gall of Breslau suggested in 1872 that some of the minor planets might be got to repay astronomers for much disinterested toil spent in unravelling their motions by lending aid to their efforts towards a correct celestial survey. 10 or 12 come near enough and are bright enough for the purpose. In fact, the absence of sensible magnitude is one of their chief recommendations, since a point of light offers far greater facilities for exact measurement than a disk. The first attempt to work this new vein was made at the opposition of Phocea in 1872, and from observations of Flora in the following year at 12 observatories in the northern and southern hemispheres, Gall deduced a solar parallax of 8.87 minutes. At Mauritius in 1874, Lord Lindsay and Sir David Gill applied the diurnal method to Juno, then conveniently situated for the purpose, and the continued use of similar occasions affords an unexceptionable means for improving knowledge of the sun's distance. They frequently recur, they need no elaborate preparation. A single astronomer armed with a heliometer can do all the requisite work. Dr. Gill, however, organized a more complex plan of operations upon Iris in 1888 and upon Victoria and Sappho in 1889. A novel method was adopted. Its object was to secure simultaneous observations made from opposite sides of the globe just when the planet lay in the plane passing through the centre of the earth, and the two observers, the same pair of reference stars, being used on each occasion. The displacements caused by parallax were thus in a sense doubled, since the star to which the planet seemed approximated in the northern hemisphere showed as if slightly removed from it in the southern, and vice versa. As the planet pursued its course, fresh star couples came into play during the weeks that the favourable period lasted. In these determinations only heliometers were employed. Dr. Elkin of Yale College co-operated throughout, and the heliometers of Dresden, Göttingen, Bamberg, and Leipzig shared in the work, while Dr. Auwers of Berlin was Sir David Gill's personal coadjutor at the Cape. Voluminous data were collected. Meridian observations of the stars of reference for Victoria occupied 21 establishments during 4 months. The direct work of triangulation kept 4 heliometers in almost exclusive use for the best part of a year, and the ensuing toilsome computations, carried out during 3 years at the Cape Observatory, filled 2 bulky tomes with their details. Gill's final result, published in 1897, was a parallax of 8.802 minutes, equivalent to a solar distance of 92,874,000, and it was qualified by a probable error so small that the value might well have been accepted as definitive but for an unlooked-for discovery. The minor planet Eros, detected August 14, 1898, was found to pursue a course rendering it an almost ideal intermediary in solar parallax determinations. Once in 30 years it comes within 15 million miles of the earth, and although the next of these choice epochs must be awaited for some decades, an opposition too favourable to be neglected occurred in 1900. At an international conference, accordingly, held at Paris in July of that year, a plan of photographic operations was concerted between the representatives of no less than 58 observatories. Its primary object was to secure a large stock of negatives showing the planet with the comparison stars along the route traversed by it from October 1900 to March 1901. And this at least was successfully attained. Their measurement will in due time educe the apparent displacements of the moving object as viewed simultaneously from remote parts of the earth, and the upshot should be a solar parallax adequate in accuracy to the exigent demands of the 20th century. The second of the 19th century pair of Venus transits was looked forward to with much abated enthusiasm. Russia refused her active cooperation in observing it, on the ground that oppositions of the minor planets were trigonometrically more useful, and financially far less costly; and her example was followed by Austria, while Italian astronomers limited their sphere of action to their own peninsula. Nevertheless, it was generally held that a phenomenon which the world could not again witness until it was 4 generations older should, at the price of any effort, not be allowed to pass in neglect. The persuasion of its importance justified the summoning of an international conference at Paris in 1881, from which, however, America, preferring independent action, held aloof. It was decided to give Delisle's method another trial, and the ambiguities attending and marring its use were sought to be obviated by careful regulations for ensuring agreement in the estimation of the critical moments of ingress and egress. But in fact, as M. Puiseux had shown, contacts between the limbs of the sun and planet, so far from possessing the geometrical simplicity attributed to them, are really made up of a prolonged succession of various and varying phases, impossible either to predict or identify with anything like rigid exactitude. Sir Robert Ball compared the task of determining the precise instant of their meeting or parting to that of telling the hour with accuracy on a watch without a minute hand, and the comparison is admittedly inadequate, for not only is the apparent movement of Venus across the sun extremely slow, being but the excess of her real motion over that of the earth, but 3 distinct atmospheres, the solar, terrestrial, and Cytherean, combine to deform outlines and mask the geometrical relations which it is desired to connect with a strict count of time. The result was very much what had been expected. The arrangements were excellent, and were only in a few cases disconcerted by bad weather. The British parties, under the experienced guidance of Mr. Stone, the late Radcliffe observer, took up positions scattered over the globe from Queensland to Bermuda. The Americans collected a whole library of photographs. The Germans and Belgians trusted to the heliometer. The French used the camera as an adjunct to the method of contacts. Yet little or no approach was made to solving the problem. Thus, from 606 measures of Venus on the sun, taken with a new kind of heliometer at Santiago in Chile, M. Houzeau of the Brussels Observatory derived a solar parallax of 8.907 minutes, and a distance of 91,727,000 miles. But the probable errors of this determination amounted to 0.084 minutes either way. It was subject to a more or less of 900,000, or to a total uncertainty of 1,800,000 miles. The probable error of the English result, published in 1887, was less formidable, yet the details of the discussion showed that no great confidence could be placed in it. The sun's distance came out 92,560,000 miles, while 92,360,000 was given by Professor Harkness's investigation of 1,475 American photographs. Finally, Dr. Auwers deduced from the German heliometric measures the unsatisfactorily small value of 92,000,000 miles. The transit of 1882 had not then brought about the desired unanimity. The state and progress of knowledge on this important topic were summed up by Faye and Harkness in 1881. The methods employed in its investigation fall, as we have seen, into three separate classes: the trigonometrical, the gravitational, and the phototachymetrical, an ungainly adjective used to describe the method by the velocity of light. Each has its special difficulties and sources of error. Each has counterbalancing advantages. The only trustworthy result from celestial surveys was at that time furnished by Gill's observations of Mars in 1877. But the method by lunar and planetary disturbances is unlike all the others in having time on its side. It is this which Leverrier declared with emphasis must inevitably prevail, because its accuracy is continually growing. The scarcely perceptible errors which still impede its application are of such a nature as to accumulate year by year. Eventually, then, they will challenge, and must receive a more and more perfect correction. The light velocity method, however, claimed, and for some years justified, M. Faye's preference. By a beautiful series of experiments on Foucault's principle, Michelson fixed in 1879 the rate of luminous transmission at 299,930, corrected later to 299,910 kilometers a second. This determination was held by Professor Todd to be entitled to 4 times as much confidence as any previous one, and if the solar parallax of 8.758 minutes deduced from it by Professor Harkness errs somewhat by defect, it is doubtless because Glasenapp's light equation, with which it was combined, errs slightly by excess. But all earlier efforts of the kind were thrown into the shade by Professor Newcomb's arduous operations at Washington in 1880 to 1882. The scale upon which they were conducted was in itself impressive. Foucault's entire apparatus in 1862 had been enclosed in a single room. Newcomb's revolving and fixed mirrors, between which the rays of light were to run their timed course, were set up on opposite shores of the Potomac, at a distance of nearly 4 kilometres. This advantage was turned to the utmost account by ingenuity and skill in contrivance and execution, and the deduced velocity of 299,860 kilometres equals 186,328 miles a second, had an estimated error, 30 kilometres, only 1/10 that ascribed by Cornu to his own result in 1874. Just as these experiments were concluded in 1882, M. Magnus Néron of St. Petersburg published an elaborate investigation of the small annular displacements of the stars due to the successive transmission of light, involving an increase of Struve's constant of aberration from 20.445 minutes to 20.492 minutes. And from the new value, combined with Newcomb's light velocity, was derived a valuable approximation to the sun's distance, concluded at 92,905,021 miles. Parallax equals 8.794 minutes. Yet it is not quite certain that Néron's correction was an improvement. A differential method of determining the amount of aberration, struck out by M. Loewy of Paris, avoids most of the objections to the absolute method previously in vogue, and the upshot of its application in 1891 was to show that Struve's constant might better be retained than altered, Loewy's of 20.447 minutes varying from it only to an insignificant extent. Professor Hall had, moreover, deduced nearly the same value, 20.454 minutes, from the Washington observations since 1862 of Alpha Lyrae Vega, whence, in conjunction with Newcomb's rate of light transmission, he arrived at a solar parallax of 8.81 minutes. Inverting the process, Sir David Gill in 1897 derived the constant from the parallax. If the earth's orbit have a mean radius, as found by him, of 92,874,000 miles. Then he calculated the aberration of light. Newcomb's measures of its velocity being supposed exact, amounts to 20.467 minutes. This figure can need very slight correction. Professor Harkness surveyed in 1891, from an eclectic point of view, the general situation as regarded the sun's parallax. Convinced that no single method deserved an exclusive preference, he reached a plausible result through the combination, on the principle of least squares, that is, by the mathematical rules of probability, of all the various quantities upon which the great datum depends. It thus summed up and harmonized the whole of the multifarious evidence bearing upon the point, and as modified in 1894, falls very satisfactorily into line with the Cape determination. We may then at least provisionally accept 92,870,000 miles as the length of our measuring rod for space, nor do we hazard much in fixing 100,000 miles as the outside limit of its future correction. End of Chapter 6.